IoT concepts. This topic explores how smart devices connect and communicate across networks to enable intelligent automation and control. Imagine a smart home where lights, cameras, and thermostats all talk to each other. That's the Internet of Things in action. IoT is transforming industries with data-driven automation, but it also introduces new risks from device diversity and weak defaults. Understanding how IoT devices interact helps assess potential attack paths and entry points in a networked environment. IoT includes smart TVs, sensors, medical equipment, and more, often managed via cloud platforms or mobile apps. Security flaws in any of these components can expose personal data or allow lateral attacks. By mastering IoT architecture, professionals can uncover vulnerabilities and design safer deployments. Attackers exploit weak configurations to pivot or spy. Defenders need visibility, segmentation, and strong authentication to secure IoT. In short, IoT is the new digital frontier, where convenience and connectivity must meet security by design. IoT attacks. This topic focuses on how threat actors compromise smart devices to access data, control systems, or launch further attacks. Picture a burglar using a universal remote to unlock every smart door in a neighborhood. IoT attacks often succeed due to poor authentication, exposed APIs, and outdated firmware across countless interconnected gadgets. Attackers scan networks for vulnerable IoT endpoints to hijack or use as footholds. Common tactics include brute forcing credentials, exploiting default settings, or leveraging exposed services and ports. Once compromised, devices can leak data, spy on users, or act as bots in a DDoS swarm. Every weak smart device is a potential attacker-controlled node. Understanding these vectors helps defenders implement segmentation, patching, and monitoring to harden IoT systems. Whether it's a baby monitor or an industrial sensor, attackers see every connected device as a door, one you must lock securely. IoT hacking methodology. This topic outlines the step-by-step process of identifying, analyzing, and exploiting vulnerabilities in connected smart devices. Think of it like picking a digital lock. Scout the door, examine the lock, then break it open. Hackers follow structured phases: discovery, fingerprinting, vulnerability assessment, and eventual exploitation. In practice, we begin with device discovery, identifying exposed IoT services over the Internet. Using tools like Shodan, attackers search for vulnerable device banners and configurations. These scans reveal IPs, ports, firmware versions, and device types, exposing easy targets. Results confirm the presence of exposed devices that may be exploitable through weak security. Attackers gain initial access this way, while defenders must scan and secure their own surfaces. This structured approach enables precision attacks on the most fragile points in IoT ecosystems, a methodology defenders must study and counter. IoT attack countermeasures. This topic covers essential defensive strategies to protect IoT devices from compromise and unauthorized control. Think of it like securing your home. Lock the doors, hide the valuables, and install alarms. IoT devices lack robust defaults, so defense starts with hardening and proactive monitoring. Admins should disable unnecessary services, change credentials, update firmware, and segment networks by device type. Tools like IoT security gateways can monitor traffic anomalies and enforce access control policies. These measures limit exposure and catch suspicious behavior early, before an attack spreads. Countermeasures help detect lateral movement, unauthorized connections, or mass scans targeting vulnerable devices. Attackers exploit weak surfaces. Defenders reduce risk by shrinking and monitoring those surfaces. Ultimately, IoT defense means treating every smart device as a potential asset and liability, and protecting it accordingly. OT concepts. This topic introduces operational technology, systems that monitor or control physical devices and infrastructure. Think of it as the brain behind a power plant: sensors, switches, and logic controllers working in harmony. Unlike IT, OT focuses on reliability, safety, and uptime, making security a specialized concern. SCADA, PLCs, HMIs, and RTUs all form the backbone of OT environments in factories, power grids, and water plants. These systems connect via field protocols like Modbus or DMP3, often running legacy software. They control pumps, pressure levels, and robotic arms. Any compromise can cause real-world disruption. Understanding OT components and protocols is vital for securing critical infrastructure. While attackers seek to cause sabotage or steal industrial secrets, defenders must ensure operations remain safe and stable. OT security is about protecting both data and machines, where the virtual world directly impacts the physical. OT attacks. This topic explains how adversaries target industrial environments to disrupt operations, damage systems, or steal proprietary data. Imagine a hacker tripping circuit breakers in a city just by sending network commands. That's OT risk. OT systems weren't designed for security. Attackers exploit that by using malware, exploits, or remote access. Typical attacks include Stuxnet-style sabotage, command injection, or hijacking human-machine interfaces, HMIs. Many attacks begin with phishing or lateral movement from IT networks into OT domains. Attackers may open valves, shut down turbines, or override sensors, all without physical presence. These disruptions aren't just digital. They can cripple infrastructure or endanger lives. That's why defenders must treat OT differently. Isolate it, monitor it, and patch vulnerabilities with caution. Every exposed control system is a target, and OT attacks are no longer hypothetical. They're a critical national threat. OT hacking methodology. This topic walks through how attackers identify and exploit weaknesses in industrial control systems using structured steps. Imagine infiltrating a factory's nerve center, carefully probing until you find the control switch. OT attacks begin with reconnaissance, then fingerprinting of controllers, and often end with command injection or manipulation. We start by discovering PLCs and identifying models, firmware, and open services. Using Snap7, we scan local networks for Siemens devices that respond to industrial protocols. The results show specific controller types and configuration details, essential for crafting targeted payloads. With this insight, attackers can take control, while defenders must monitor traffic for unusual scans. Understanding this methodology gives defenders a roadmap of likely attacker actions and lets them build proactive defenses. Precision is key in OT, both for attackers who aim to disrupt and defenders who must prevent catastrophe. OT attack countermeasures. This topic outlines defensive practices to secure critical infrastructure from cyber attacks targeting industrial systems. Think of it like installing circuit breakers and watchdogs inside a power grid. Prevention with resilience. OT environments can't tolerate downtime, so security must balance protection with continuous operation. Countermeasures include network segmentation, air gapping, strict firewall rules, and protocol-aware intrusion detection systems. Tools like SCAD Offense or Nozomi networks monitor ICS traffic for abnormal behavior. These systems alert defenders before attackers gain full control, reducing response time and risk. Detection of unauthorized scans, changes, or remote commands is the first line of defense. Attackers seek operational disruption, so defenders must enforce visibility, patching, and risk-aware policies. Industrial control systems are vital, and their protection requires specialized tools, trained staff, and relentless vigilance.